Hello everyone, welcome back. Today we have 208 implement trie or a prefix tree. A trie, pronounced as trie, or prefix tree is a tree data structure used to efficiently store and retrieve keys in a dataset of strings. There are various applications of this data structure such as autocomplete and spell checker. So we are going to implement a trie class with a trie, which initializes the trie object. We have a method insert, which takes in a string word and inserts the string word into the trie. We also have a search method, which given an input word returns true if the string word is in the trie, if it was inserted before, or false otherwise, along with another method starts with, which takes in a word. However, though similar to search, this returns true if there was a previously inserted string word that has the prefix of this. However, it's not necessarily the end. So if we have apple, app is a prefix that's within apple. And app is also a full word on its own. But if we had, you know, app, AP, let's say we had AP, then AP is a prefix. However, it is not the full word. So AP will return false for both. APP will return true for search and true for starts with as well. So AP will return true for starts with, whereas APP will return true for both starts with and search. Okay, so let's look at an example here. And we have three methods, right? To insert, to search, and then check if it starts with. So the first thing we do need is a node that can represent a single trie node. So let's initialize that to begin with. So let's say we have a class trie node, and this one we have to track two things. One is where else it's pointing to for the next char, and also if that current node represents the end of a string. So let's initialize, and we do care what children or what chars this points to. That can be a dictionary, and also a Boolean value of whether this at its current position is complete or not. Complete as in it ends the current word or not. And when we do the insert first, we can follow this. We create a trie, and we're going to insert apple. The way we insert apple is by adding there's a root node, which is way at the top, and this will basically have no value. If you notice here, the node itself doesn't have a value per se. It has children and whether or not it represents a complete state. So this root, let's just call it empty, will point to different children. The first of which will be an A. So let's add the A. A doesn't have any children, so we can add a P. P, no children, so another P, another L, and an E. And here we'll say this one is a truth. This is the end of a word. Okay, great. Now when we search APPLE, we're going to start at the root and say, is A here? Yes, here. Is P here? Yes, P is here. So we got the A, we got the P, the next P, yes. The next L, yes. And the next E, yes. And is this the end of a word? Yes, it is. So this is going to return a true. The next is a search. When we search for app, notice we expect it to return false the first time because we're going to start from the root. Is A one of the children? Yes, it is. So we got the A over here. P, yes, it is. P has a child, P as well. So there you go. However, we reach the end. This is a complete word, but this is not the end of a word. Like this guy. This is not the end. So this will return false. And so that returns false. However, if we search for starts with, this will indeed return true because we're going to search. We're going through the same process. However, here, instead of checking if this is an end of the word, we just say, yes, we were able to exhaust this. We don't know if this is the end of the word, but we're at the end. We made it through, so this is going to return true. Whenever we insert or initialize, it's a null. We don't return anything. So, but here it gets interesting. We are now inserting app, in which case we check first, is A one of the children? Yes. So we don't need to duplicate A. All right, we got the A, great. P, is P a child? Yes, it is. No need to duplicate there, great. P is also a child, no need to duplicate. And this is the end of the word. So finally, for the first time, we're going to mark this as true. Yes, I am an end. I am complete over here. Just like this one. Yes, I'm also complete over here. Then when we search this time, well, guess what? We have the A, okay? We have the P, okay, and we have the P. But what makes this search different from this search is that now, because we inserted and flipped this to true, indicating that this is a complete state, now we can return true. Now, let's say we have a word like 8, okay? The only difference here is yes, the first one is a child, so no need to duplicate. However, there's no T. So this child will no longer just be P, but it will also have a T. And then T doesn't have any children, so we can add the E and mark this as, yes, end of the word. All right, so let's now implement this. Okay, we have the children and we have whether it is a complete state onto its own. So when we initialize, what did we need? We needed the root. That's all we needed to initialize this. So let's say that we have a root, which itself is just nothing more than a trie node, which is this guy. Okay. And what did we do when we inserted? We first check if there are keys, and because we don't want to duplicate, so that's fine. Let's say, let's first have a little pointer that points to self.root. And we'll say for every char in word, we ultimately want to go down the tree, but we first want to check if char is not then cur.children. If it's not already its children, then only do we want to insert it. So let's say cur.children. Cur.children is, where are you? Is a dictionary. We're initializing as a dictionary. So cur.children FCH, which is the current char. We're going to initialize it as a new trie node. All right, so we're initializing one of these new guys. Okay, and it'll default to having no children of its own, and its complete state is false. And this is only if we're not duplicating, if the char is not already a child. Okay, and once we have that, we just move our pointer to cur.children of that char. So we'll just continue moving down this tree. Okay, and once we do that, we can say, hey, we're at the end. I'm at the last char, and I want to mark myself as complete. So I can say cur.complete. I am now complete. There you go. And this returns nothing, so we're done. So this one's done, and now let's move on to search. So when we search, it was a similar process to inserting, where we check the first immediate children, starting from the root. Do we have children? That represents the first character. If we don't, then we return false. Our search is false. If we do, then we keep going down that line. And at the end, we check, is it the end? Have we reached the complete word? Okay, so let's also have a pointer for this one that points to self.root. And say for a char in the word that we're searching for, we're going to say, hey, if this char is not in cur.children, you know what? Something's not right. We couldn't find it, so just return false immediately. Otherwise, we continue to cur.children of this char. Then at the end, keep in mind, we care if it's a full word. So not only do we return true, but we return is the current char, the last char, complete? And that matters. Which leads us to our last method. Our last method is really similar. In fact, we can pretty much copy the whole thing. But can you guess what we need to change? Can you see here? We have an end, whereas when we did a starts with, we did not care if it was an end or not. So the only thing here that changes is true. And of course, we just update these variables. So it's no longer a word, it's a prefix. And yeah, I think that's pretty much it. So let's try running that and see how that goes. Okay. And we do want to submit. And there you have it. Decently efficient. And I don't know if I did a good job, but this was somehow so hard to understand initially, but like once it clicked, it just clicked. It made complete sense. I hope the drawing helped. The main thing to wrap the head around is that this node itself doesn't really store anything. Initially, I was thinking, okay, what's my current value? It's a char, and then I have something. That's not the case. And this node doesn't store anything. It stores its children. Its children will have additional, chars, which itself will be, excuse me, a node, which again doesn't have any value onto its own. It itself will store its children and whether or not it is complete. And yeah, there you have it. 208 implement trie prefix tree. Thanks so much again. Happy coding, and see you next time.